time. So we're identifying within hospital over time. And then our interpretation is, because we're looking over time, we're explicitly controlled. Our coefficients are then interpreted as changes rather than as levels. So where we might say, if we weren't controlling for time, or something like the level of insurance, hospitals with higher uninsured rates have lower drug extent use. By going to this fixed effect, hospital fixed effect, time, year fixed effect analysis, we're saying hospitals that experience increases in drug extent use are experiencing increases in uninsured patient shares are experiencing decreases in drug extent use. And how do we do this in Stata? So again, in our context of suppose we have doc and year fixed effects here. The syntax is exactly the same as what I showed you on the other page. Even though we tell Stata we have doc ID and year as the two dimensions of our panel, in all cases we have to add controls for year to the model specification. Stata doesn't have a feature to do two-way fixed effects automatically. It's not hard to do that. This I feature says replace the category with a set of dummy variables to control for each one explicitly. Notice that is not the same thing as putting in C.year, or just year on its own, where then with year on its own we'll be controlling for trend, linear trend in year, but we're not getting the fixed effect aspect of year because only the dummy variables will do that, not the trend. You can control for trend, it might make sense to do so, but you're not getting the fixed effect interpretation as a result of that. All right, so everything I've said up till now is really applicable primarily, or really only, to linear models. So a lot of reason why I think fixed effect models are not that popular in the biostats and epi world is that the economists are relatively more willing to use linear models in cases where you don't necessarily have continuous dependent variables. Like where I said the statisticians and the epidemiologists would estimate logit models, the economists would say let's estimate a damn linear probability model because that lets us use fixed effects and lets us easily interpret differences. So what about those of us who are trapped in the middle and may have swings one way or the other but still want to use fixed effects in nonlinear models? Well, the underlying problem is what's called an incidental parameters problem. There's basically this idea that that the estimates from your models will only be consistent if the number of fixed effects is not expanding proportional to the number of observations you have in the data set. So if you have, let's say you have a data set of hospitals and only a few years of data for a lot of hospitals. And if the data generating process or the underlying idea is that if the data set is expanding, it's expanding on the hospital margin, so you're getting more, as the data set were to increase, it would be increasing by adding hospitals, then you're adding fixed effects as you're increasing the data set. So you never get, sort of in the limit, you don't get enough observations per hospital because there's never a point at which you're going to start getting more observations per hospital because you're always adding hospitals instead of adding years of data per hospital. It's a theoretical argument. The issue is, with the incidental parameters problem, the fixed effects are not identified, the coefficients of the fixed effects are not consistently estimated. In the linear model, that's not a problem. There's no spillover. If the coefficients, specifically in a linear model, if the fixed effects are estimated inconsistently, that's okay because the coefficients that you care about on insurance type or whatever, those are still going to be pure. But in a nonlinear model, everything changes, and there's all the spillover because it's a nonlinear model where you're now saying, okay, the coefficient of consistency, if there's even a single coefficient that's estimated inconsistently in a nonlinear model, then all of them are at risk for being estimated inconsistently. So that's why we can't just add 1,000 dummy variables to a logit model. Or can you? So that is a source of so let me back up. How would you estimate fixed effects models using logit if you wanted to? So there are three basic approaches. None of them is perfect, not surprisingly, because we're basically trying to retrofit an estimation technique that isn't built well for fixed effects. Our first option is to do what's called unconditional fixed effects. That is, add those dummy variables. Just like we did with regress. Instead of regress, we use logit. We add 1,000 dummy variables, one for each position. Here the issue is then how many observations you have per unit. If you have got lots of observations per unit, say 50 or 100, you're probably in pretty good shape. If you've got 2 or 3, you're almost surely in bad shape. And so it's going to be, it's the kind of thing where if you say, I ran an unconditional fixed effects logit model, the knee-jerk reaction is say, but you can't do that because incidental parameters problem will mean your results are all crap. So then you've got to go through the exercise of playing defense and saying, okay, well, if you're going to do that, then you've got to cite simulation. Paul Allison's done some simulation studies to say, like, with X number, with this many observations per fixed effect, we can be fairly confident, that this really isn't a problem. You may want to estimate your models another way and make sure that they're stable. And these models are a pain in the ass because everything that's a pain in the ass about them in the linear model sense of having to estimate a single coefficient per fixed effect is even worse because it takes longer in a nonlinear model. Logit estimation technique is slower. So then option 2 is what's called conditional fixed effect. This takes advantage of a specific feature about the logistic function that enables us, Stata, to make those coefficients disappear. We can't get estimates of them, but we can control for them by conditioning them out of the likelihood. What does that mean? I'm not entirely sure. The pragmatic aspect is that you can't estimate these models in Stata, and you're okay doing it. They're just really ornery models to estimate. If you've got a lot of data like you've got one of these big data sets, you try to estimate these C-logit, or you can estimate it with X-logit with fixed effects. Be prepared, if you've got a lot of things you're controlling for, be prepared for a long time of Stata trying to do something and then telling you the model didn't converge, so tough. Which is highly frustrating and may lead you to go back to here. But here, you can do conditional fixed effects when you've only got a handful of observations per unit. You can do it here, but you're going to run into, you might sneak it through, but it's not the right thing to do. Then the last thing I want to talk about before we end today is Paul Allison's hybrid approach, which I've played with myself and found it to be pretty, it's a nice kind of like try to have your cake and eat it too, in a way that's a little bit better than the conditional fixed effects. Or the unconditional fixed effects. And it works with more models than just logit anyway. So here again, we'll start with our typical panel setup. And then, but whereas what we're going to do differently this time, we're going to leave the dependent variable as its original form, as y sub it. That is, the value for physician I in year t. We're modeling that thing as a function of just for the time-varying covariance or unit-varying covariance, we're going to subtract the mean x bar sub I, that is, if this is hospitals, then the hospital-specific mean from each observation at the patient level within the hospital for each of these patient-varying characteristics, and then also add the mean to the estimation equation. We don't need, and unlike with regular fixed effects, we can actually add in hospital invariant characteristics that we can observe. So we now get estimates of C, the coefficients on those hospital invariant characteristics, time invariant characteristics that we didn't get from the model. Now, the important thing to note here, and I've kind of screwed this up myself, is if you've got 30 variables, say you're controlling for a bunch of comorbidities at the patient level, and they vary across patients within the hospital, you have to then control for each of those 30 variables plus the 30 hospital-specific means as well. You can't cherry pick out, or you're not getting the full benefit, I guess, or there's some risk that you're. The right way to do it is to control for all the means of all time-varying or within unit-varying characteristics. And then you probably want to do a random effects model to account for the correlation across observations within a unit. Now that was the Paul Allison pure approach. These guys, Meg and Paradies, have a reasonably compelling article, compelled me anyway, enough to write the slide, to tell you that rather than doing the difference between xit and x bar and then x bar, just control for xit itself. And that enables you to interpret the coefficient b2 somewhat better, because you're now explicitly controlling for the individual specific value rather than the delta between the two. So, shoot, I'm running over time. Sorry, guys. What are the implications? Actually, no. Let me just. I don't want to run through this too fast. I'll come back and finish off the hybrid approach on Tuesday and make sure we have a chance to talk about it before talking about internal variables. Thanks very much. Have a good weekend. I'll see you next week.